Good day, welcome back to another episode of Extractions&Ire, and today's project is to make a yellow pigment, which comes from a 2019 paper about making environmentally friendly yellow pigments. And as we have been doing recently, we're going to start from the raw materials of the periodic table. So I just have samples of the metals from the periodic table, and we're going to be doing chemistry with them to try and make this yellow pigment. This 2019 paper makes two yellow pigments. They make a tantalum-doped yttrium molybdate and a terbium-doped yttrium molybdate. And you can see why I want to do this. This is really feels like a random scatter shot of some of the most obscure elements in the periodic table. Tantalum, yttrium, molybdenum. We're going to be looking at why the authors would want to do that, and if this is even achievable in my home lab, which I'm not entirely sure about. But first of all, what do I want to make this? What do I get out of making a yellow pigment? Long-time viewers of Extractions&Ire and Explosions of Fire will know that there's this big superstition around the colour yellow. If we go to which Wikipedia page, synthesis at any point goes yellow, it just stops working, alright? First of all, it does go a horrible yellow colour, which is never what I want to see. Seriously, the more yellow this goes, the more likely it is just to blow up at any moment. It's come up so many times across the years, but people often comment, well, if yellow is a bad sign, but you're trying to make something yellow, does it work? Am I really good at making things yellow if things naturally want to go yellow? Or if I actually want to make something yellow, will it go a different colour? So today we're going to find out by making this yellow pigment. We're mainly going to be focusing on this tantalum-based one, but if the tantalum one doesn't work, which we'll talk about in a sec, but if that doesn't work, we'll go with the terbium-based one. But these are some fun, obscure elements that I don't see chemistry done on all that often, so this will be good fun. So what's this 2019 paper all about? Why are people trying to make new pigments? Well, making pigments, it seems quite hard because you need a pigment to be stable both long-term, out in the environment, in the UV, you want it to stay the same color and not fade over time. But also a lot of pigments need to survive being heated to high temperatures because if you wanted to color pottery or ceramics, often you need to do that before firing the pottery. So your pigment has to survive getting heated to 1100, 1200 degrees while the pottery gets fired without getting completely destroyed. So you can't use organic molecules for this because, organic dyes and that kind of thing will just absolutely burn up at those pottery temperatures. So you need to rely on inorganic dopants or inorganic materials, really. This is not a particularly hard thing to do, and humanity has been coloring pottery and firing it for potentially thousands of years. It is just harder to do if you don't want to use lead. Once again, it comes up in most of my videos. You can just use lead and it works really well. You get some nice yellows, some awful yellows, vibrant reds, all from lead. But if we want to do it without lead and without toxic hexavalent chromium and maybe without cadmium, we don't have as many options, unfortunately. So recently there's been a lot published on molybdate. So molybdenum is underneath chromium, so it has, sort of similar chemistry to chromium. They are very stable molecules. Once you get molybdenum oxide or molybdates, they can be extremely stable. And also they have very low near-infrared absorption, which is good for this concept of like cooling paints, where if you paint something in the sun and you don't want it to get so hot, if the pigment reflects a lot of that infrared light, it won't get as hot. And also you're using non-toxic elements, and that's kind of the concept of making it environmentally friendly. I'm not entirely sure I buy this argument too well for this particular material. Like, sure, it might be environmentally friendly once it's made, but these elements, yttrium, tantalum, terbium, take enormous amount of energies to refine, and tantalum in particular is one of the most conflict minerals or conflict elements in the world, and to suggest that you can make a widespread pottery glaze that's environmentally friendly using tantalum is, it's a bit of a reach. Actually, here's an interesting thing about the economics of tantalum. So Australia has huge reserves of tantalum, and we used to do heaps of mining of tantalum pre-2008 because for some reason the stock market crash of 2008 closed all of Australia's tantalum mines, but there's still demand for tantalum across the world. It's used very heavily in capacitors. So that demand was entirely filled out of West Africa. And now Australia can't open any more tantalum mines because it's not economically viable, because we have to compete with child slaves for some reason. I don't know how this happened. Oh, and also, one other thing I find is sort of in conflict with its environmentally friendly headline is that you need to heat this pigment up to 1400 degrees Celsius to get the synthesis to work. Industrially heating things to 1400 degrees C, very, very difficult. In fact, it's very, very difficult even on the lab scale. This paper heats it to 1400 degrees C for 6 hours. Just because it doesn't have lead in it doesn't mean it's immediately environmentally friendly. Like, come on. We've got to try a little bit harder than this. Oh, actually, sorry, the editor's note. In fact, when you read 1400 degrees C, you think that maybe they're just heating that because that's the maximum thing of their furnace and they don't need to go that hot. But the paper specifically shows that 1300 degrees is not hot enough and you need to go to 1400 degrees because the reaction, the solid state reaction, doesn't go to completion if it's at 1300 degrees and doesn't happen at all at 1200 degrees. A weird note is that I thought this data was from the paper, and I was rereading the paper today ahead of this, and the data's not in there. And then I realized that the authors has published a virtually identical article 3 years earlier in 2016, except using zirconium as the fucking dopant. Once again, making yellow pigments, and it is a completely separate paper. None of the data is plagiarized between the two of them, but it's blow for blow exactly an identical paper, but it's only cited in the method section as like, oh, it's used similar methods, which is like stupid. Sorry, no one's forcing me to do this work, but we got to talk about this one weird thing about this huge weird thing. I mean, look at the colors of the yellows, like with all the dopant. On the end here, there's no dopant in there, and it's still yellow. In fact, it's pretty much exactly the same yellow, no matter how much tantalum or zirconium you put in there. The terbium one slightly changes color, but like you go to all this effort to put zirconium and tantalum into this yttrium molybdate, color just looks exactly the same. I don't know. So we will maybe make an undoped one as well and just see visually with my eyes and the camera, is the doped one actually any different yellow than the undoped one? Anyway, let's talk about the synthesis. So I've mentioned that we're starting from the raw metals, so the pure metals themselves, and we need to convert them to the oxides. And once there are the oxides, this is where the paper synthesis begins, and the paper synthesis is basically mixing up the oxides in the correct ratio and heating it to 1400 degrees for 6 hours. I very recently bought a new furnace in a recent video, and that furnace was very good. This furnace only goes up to 1100 degrees Celsius. 1400 degrees is very hot, so we will have to get a different furnace, a second brand new furnace for this video. How do we get to the oxides? Going from yttrium metal to yttrium oxide should be relatively easy because yttrium is quite reactive, and I just have this big slab of yttrium now. And same with molybdenum. Actually, maybe not. Molybdenum is not very reactive. I think nitric acid should be able to corrode and dissolve the molybdenum metal, and then I think it should be easy enough to get to the oxide from the dissolved molybdate oxide species that dissolves in acidic solution. Molybdenum chemistry is a little weird, so it might get a little bit difficult. Speaking of difficult, tantalum is extremely non-reactive. It doesn't get corroded by any acids really at all, short of hydrofluoric acid, which is not something I can do in my lab. I can't do HF. So I don't really know how we're going to dissolve some tantalum enough to get some oxides. I will try a few things. If none of that works, we will stop making the tantalum doped one, and then we will get to doing the terbium doped one, because terbium, like yttrium, is quite reactive, so it should be easy enough to get terbium oxide. But I want to do the tantalum. I want to crack tantalum open and get it reacting. Just because I have a lot of enthusiasm for this task doesn't make it any easier. It makes it slightly easier, the enthusiasm, but it's hard to bend science to your will, as much as I fucking try. Anyway, that's the project. So if we do this all well, we'll end up with a yellow pigment that should be yellow for all eternity. If we do it badly enough, I guess I'll burn my house down, but that's not really... Why don't we start with the molybdenum? Where's my bloody molybdenum samples? Let's start with there. All right, here we have some molybdenum metal. You can see it's got that classic blue little shine on it, a bit of oxide layer. Molybdenum loves forming these blue colors, but we're not here to form blue colors, we're here to form yellow colors. So this is 30 grams of molybdenum metal. There is 17 of these pellets, just for those people who really love numbers. Yeah, very dense metal. I can't shake this too hard or I'll end up shattering the beaker. We are trying to dissolve this in nitric acid. It might react quite violently, it might not react quite violently. In fact, it might not react too much at all. Nitric acid is very oxidizing, so it'll oxidize the molybdenum, but that might form an oxide coating that sort of stops the metal from reaching the acid again. So that's passivation. If it passivates, then this starts to go very slow and can stop completely, which we don't want. Hopefully it dissolves. It's probably going to fume a little bit or quite a lot of horrifically toxic nitrogen dioxide gas. She'll be right. Okay, let's get this dissolving. All right, it's been about 10 minutes. Yeah, we're definitely getting corrosion of the metal. Not at a very high rate though, and there is a lot of nitric acid there. So I've seen some reports aqua regia does react very fast with molybdenum. So aqua regia is a combination of nitric and hydrochloric, which is usually used to dissolve gold. This will help. I think that powder in there is what we want. Once we dry it out, it should be molybdenum trioxide. It's kind of a bit hard to work out exactly the chemistry of all this, but I think once we add a little bit of hydrochloric, it's also going to dilute it a little bit, give it a bit more water, which may help with initially dissolving this oxide layer and keep this stuff reacting, because the hydrochloric acid here is only about 25%, whereas this nitric is 70%. Let's give that a shot and see if it picks up reaction speed a little. Oh yeah, it's bubbling. Ooh, we're cooking now. Okay, it's blue now. It was red, and then when I heated it, it went yellow, and then I kept heating it, and now it's blue. I mean, this happened over the course of about a week and a half. The molybdenum is mostly dissolved. I've been adding a little bit of acid over the course of the week and a half, just to try and get it dissolved. It dissolves very slowly. It looks like it's dissolving fast when you put a lot of nitric acid in, but I think the nitric acid is maybe just decomposing or getting catalytically decomposed, because it puts out heaps of nitrogen dioxide gas, an unhealthy, unsightly amount of nitrogen dioxide gas, but a lot of the metal doesn't dissolve in that process. I don't know why it's blue. This is actually a very typical molybdenum blue, actually. Known for this blue color. I don't know. We're trying to make molybdenum trioxide. This is what we think is in here. It's kind of why it's all sludgy. Wikipedia lists it as a yellow solid that sometimes appears blue and green. And maybe that's what we've done here. We've made our yellow solid appear blue. That's not a great sign in our project to make something yellow. And the first thing we're trying to make that's yellow goes a vibrant blue. We'll see how we go. Molybdenum trioxide is reasonably soluble at these higher temperatures because it's heating on this hot plate here. But if I cool it down, then we might get some more to crystallize out. And it should be this nice powder that we can filter off and collect. I don't know what color it's going to be once it cools down and the solid. Could be this blue, could be green, could be a brand new color. One interesting thing is that first red color, that brick red color, I don't know what that is, and I'm not entirely convinced that anyone knows what that is. There was a post on Science Madness a couple of years ago where people were like, what's up with this red color when you put molybdenum in concentrated nitric acid? And no one could find any references to it, and you look online and people just say, yes, it dissolves to form molybdic acid, which is clear. So no idea why it goes red. It's some complex, some unknown complex that no one's figured out. Probably no one's tried. You know, you go down the periodic table to some of these slightly more obscure metals, and it's so easy to hit chemistry where people are like, oh, I don't know, it just goes red. Like, what do you mean? Like, there's probably some complex, but no one knows what that complex is. Anyway, let's get this cooled down and get this oxide out. Okay. Right, and after filtering, we've got this bluey green paste, which presumably is some sort of oxide, although I don't know why it's bluey green. We have this deep red liquid and 2.8 grams of leftover metal. So, you know, there's what, 27 grams or so of molybdenum dissolved in here. Only looks like a couple of grams of oxide, or whatever the hell this is, at the top. So yeah, all our molybdenum is still dissolved. Well, most of our molybdenum is still dissolved. We'll collect this, but then we still need to think about how we get this molybdenum out of solution as this molybdenum trioxide. Maybe I'll just boil it. Why don't I boil it? It seems to choose a different color every time I heat it up. So why don't I just boil it again? Maybe it's going to go yellow or blue or green or something. Or maybe all of them at the same time. Let's try that. Why is it blue again? What's going on? Where's all the solid? Okay, maybe it's too concentrated, maybe there's too much acid, maybe the chloride is complexing the molybdenum and that's keeping it soluble even though it's at a low pH. I'm going to try, this is just some sodium hydroxide in water. I'm going to add a tiny bit of this to the sodium hydroxide just to see if anything precipitates out. I just got to be careful here because it's a reasonably hot solution and this is concentrated, well not that concentrated base, but concentrated acid, so gentle, gentle. Okay, we had something for a moment there. So maybe if I balance the pH just right. I don't know, I'm obviously just making this up now as I go, but like, where'd the solid go? I don't know, maybe it's coming back now. It's very blue though. Am I expecting it to be blue? I don't even know what I'm expecting at this point. Alright, now it's too acidic again, I guess. Alright. Hell yeah. Okay, but what happens now if I add in a splash of nitric acid? So it's yellow, right? And that's the thing I want, right? Oh wow, oh my god, what a colour change. I'm the master of yellow. Alright, god damn, this is vibe-based chemistry, but my goodness, wasn't that a transition? I'm heating to get it dry and on some mild heat, it's losing its blue. Alright, so I've got some of that solid off, filtered off, but the stuff that came through was still brightly coloured, so I'm certain there's still molybdenum in there, and I've been trying to pH balance it so we get the most precipitation, because if we go too acidic, all the precipitate seems to redissolve, and too basic, it redissolves again. So if we hit just the right pH, lots of solid starts coming out, and I don't really know what pH that is, so I'm not really sure really what I was optimizing for, but just balancing additions of sodium hydroxide solution with nitric acid solution. Anyway, all this to say, I think I'm right on the verge. I'm just slightly too basic, so let's do it. My whole life, I've just been slightly too basic, you know? Yes, solid. Oh yeah. Fantastic. Okay, I cooled it down as well because I think it's got reasonable solubility in water. Here we go. This is what we want. Once again, a different colour. It's done every colour so far. Actually, you know what? For the sake of it, why don't we see if we can get nice crystals? Now we know we're at the right spot. Let's heat it up and then cool it back down and see if the stuff dissolves and then re-precipitates out as reasonably nice crystals. Although this powder's fine, but, you know, let's see if it looks nicer. I don't know. Might be cool. Next day. Okay, and after all this, we ended up with 3 batches of molybdenum trioxide. Well, supposedly molybdenum trioxide. We have this first batch that we filtered off that was sort of white, and then after filtering was green. We had this batch, which couldn't make up its mind. It was blue, and then it was a white suspension, and then on cooling, it's sort of turned back a little bit blue. And so the yellow and the blue really makes it a bit of a green colour. In the end of it, this second batch really looks like the first batch. I'm fairly confident that this is molybdenum trioxide. This third batch, the batch that we just tried to recrystallise, looks quite nice, apart from the fact that it's bright pink, or really orange. Some extra crystals down the bottom here. I don't know, I don't really get this. I'm not entirely convinced that this is molybdenum trioxide, although I don't really know what it is, even though that batch should have been the purest and the one that we spent the most effort on. I like this stuff, so maybe I'll stick with this second batch here. That is okay. I'm okay with this. Given this one. I thought it might have got a bit complicated, this molybdenum chemistry, and I was correct. But let's move on to something maybe a bit more simple. I'm not going to say that it's going to be simple because it never is. Anyway, the yttrium. Let's go dissolve up some yttrium. All right, are you ready to see the yttrium slab? Are you ready? Do you think you're ready? Hell yeah. Okay. It's pretty good, but maybe I shouldn't have wiped it up so much. This is, what's it say? 126 grams of yttrium. It is a dense, rather uninteresting block, but yes, a rare earth. We don't need 126 grams of metal for this reaction. I mean, we might as well do a reasonable amount of it. I don't know, maybe half. How are we going to break this up? I suppose we could nicely and gently, carefully break this up. Ooh, sparks. On second thoughts, breaking it is a stupid idea. Let's not do that. Let's get our big block into the water, and then we'll add some hydrochloric acid, and that will start dissolving it away. Let's go. Look at the slab go. Look at me slab. Beautiful stuff. Hell yeah. There's a lot of hydrogen though, so no one light any cigarettes nearby, okay? Just gonna let this hydrogen run away into space. Alright, it's been reacting for several hours, and I've been topping it up with acid. Whenever it starts to really slow down like it is now, I don't know, maybe it reaches a solubility limit. Maybe when the acid runs out, the water still reacts with the surface, but slowly, and it starts to form a bit of a hydroxide layer over the metal, which sort of protects it and slows down the reaction rate. I don't know why it's so grey though. We saw this before, I think, with the yttrium, or maybe it was the ytterbium that we dissolved, and it really went very grey. So I'm not quite sure what all this grey is, but it's not going crazy, so it's enough to kind of leave it overnight. And we'll come back to this maybe in a couple of days. If it was a bit more reactive, I couldn't leave it like this, because as it reacts, it gets hot, and then, you know, the heat makes it react faster, and then it's going, and it takes away. But this, I'm not concerned about it getting too hot. In fact, it's cooled down. Now it's not going to get any hotter, and the reaction should taper off at some point. I don't think there's enough water and acid to dissolve this huge whole block. In fact, our slab's still mostly there. There's heaps of it there, so I don't know what will stop this reaction, but we'll come back and see what it looks like in a couple of days. Okay, day 2 slab update. Slab is still there. Yeah, there's a lot of debris in this flask. Is that a good word for it? What is all this stuff, you know? Oh, who knows? Anyway, lots of slab, so I think worthwhile we add a little bit more acid and keep it cooking. Maybe give it some heat as well. Just get it restarted. Get it cooking, you know? Subscribe for more slab updates. 1 week slab update. There's still a lot of slab. I don't know, does the slab look smaller a bit today? Maybe. I think there's probably enough yttrium dissolved for this project. But once again, there's still so much of this crap down the bottom. So what I might do is, even though most of this stuff is what we want, I might re-acidify it and then filter it off, so anything that doesn't dissolve in acidic solution, like this grey stuff, oxide or some sort of parts of the metal that sort of have fallen off but haven't reacted with the acid somehow. Yeah, I'm going to re-acidify it and then filter all this crap off, and then add sodium carbonate to precipitate out the yttrium as a solid yttrium carbonate, which we can use directly pretty much as a stand-in for yttrium oxide, because it's just going to decompose into yttrium oxide under the strong heat conditions that it's going to be in. So we can precipitate out hydroxide or carbonate or anything that will easily decompose into the oxide. I'll probably go carbonate just because it tends to make solutions that are easier to filter. Bigger particles than oxide sometimes gets very sludgy, and it's like filtering paint. We can filter off this grayness, just horrible grey stuff. All that just for 26 grams dissolved. Wonderful clear solution. Bit of grey slop got rid of. Beautiful. And here is our reasonably dry yttrium carbonate. Looks like quite a bit there, not as much as we thought initially. I thought a lot of the block dissolved, but only 26 grams or so of the block dissolved. That's fine. This is great. We can go on to the next step, which is the tantalum. And I still, despite doing all this, haven't really thought about how I'm going to dissolve the tantalum. It won't dissolve in any of the concentrated acids I have. Maybe concentrated sulfuric acid if we reflux it, get it at 300 degrees and do that for many hours. Maybe we'll dissolve a little bit of it. Maybe we'll heat it and put chlorine gas over it and try and distill off some pentachloride, tantalum pentachloride. That sounds difficult. Yeah, I'll think about it. I'll come back when I have an idea. Okay, I've got it, I think. One of the few things you can't use tantalum crucibles for is molten hydroxide. So people make tantalum crucibles because they're very inert and you can take them to high temperatures and they won't react with pretty much anything. Except they specifically say that you can't use molten hydroxide. So if we react molten potassium hydroxide, one of the most corrosive substances known, with this tantalum powder, it will dissolve, hopefully. Well, it'll form some sort of potassium tantalate, which we can dissolve in hot water or dissolve in normal water, cold water if we want to, and then add some acid, and then that should precipitate out our tantalum pentoxide. That's the hope. Obviously, if we've got an incredibly corrosive substance, what container do you put it in? Because molten hydroxide will leak through glass and ceramic. I've got some stainless steel here. This is obviously not a crucible, but you know, anything's a crucible if you're poor enough. Oh, I've just put this down, ants. It's gonna be really hot. Oh, all right, I should move this. I feel bad for the ants. Will the molten hydroxide eat through the stainless steel? Yes, absolutely. And it'll form chromium and iron oxides. I think the nickel might be okay, but it's kind of a rare exception. But yes, we will have to chemically then separate the tantalum from the iron and chromium, but hopefully that shouldn't be too difficult, as both those ions should stay dissolved in acidic solution and the tantalum should precipitate out. And my hope is that if the tantalum is a powder, it will react with the molten hydroxide before we eat through the steel and leave the container. So that's the hope. Can we react the tantalum quick enough before we eat through the container? Yeah, it's on this stove because it's got to get heated to, I don't know, what's the temperature, 350 or so, which is, yeah, why it's on here. So we heat it up quickly and then should cool down quickly so we don't, once again, eat through the container. Oh my God, ants are loving this shit. Okay. You want some tantalum, ants? No? Can't spell tantalum without ant. I don't know. Is that anything? Is that anything? Are we cutting that one out? I think we cut that one out. Chuck another tantalum shrimp on the barbie. No, I can't do the Australian accent. Ooh. All right. That is hydrogen? Seems like hydrogen. Alright, I'm back up even more. You're on your own, camera. It's kind of done. I'm going to quick wire my head here rather than let it eat through the container. You can see that green from all the chromium. What do we think? I think it's particularly safe to approach, but it's been like half an hour. Milky. New alternative milk, this one. Alright, let's go steam it. Alright, this is our solution. Look, we made a yellow. It looks like we have our tantalum pentoxide maybe already suspended in the soluble tantalum species. It might just decompose in aqueous solution, but it's yellow and orange a bit, so it's probably the iron and chromium, especially even chromate, causing this yellow color in low concentration. So we'll acidify it. Hopefully everything, all the ions that we don't want go into solution. Obviously the chromate is in solution, is this yellow solution already, but we're gonna have to add a lot of acid actually. So got the nitric acid here. There's a lot of potassium in here, or potassium hydroxide. Can't just add it in all at once either. That'll be very bad. So slow additions. Man, that took hours to filter. It's like filtering paint. Something we were trying to avoid with the yttrium one, but we could not avoid it here with the tantalum pentoxide. It is not a nice white powder. It's a bit greeny grey. The fact that it was yellow and then kind of went greeny grey after drying and washing with ethanol makes me think it's a low amount of chromium contamination. I'd love to fix this. I washed it quite a bit to try and get the colour out. The chromium contamination, I feel, has the biggest potential to cause a shift in the colour of the end product, because a small amount of chromium can really change colours as a dopant. But, you know, we'll press onwards. Maybe this is just how the tantalum pentoxide is meant to look. I mean, that's not true. That's just pure denial. But there was a little bit of unreacted tantalum powder from that reaction mix. I guess the stuff that didn't really have good contact with the potassium hydroxide. There wasn't really much mixing in that reaction apart from all the hydrogen generation, which was a little bit scary. But yeah, because the tantalum metal is so heavy, I could just decant off the oxide and leave behind that tantalum metal. So hopefully there's not too much metal powder in our final product of the oxide, but I'm fairly confident that there really will be pretty minimal stuff. Yeah, it really looked like it reacted to completion as long as it had contact with the potassium hydroxide, so I really should have mixed it better before heating it, but it's good to see only a tiny little bit of metal left behind. We have the tantalum pentoxide right now, so we actually have all our ingredients. We've got our yttrium carbonate, we've got our molybdenum trioxide, and our tantalum pentoxide. So we can get to the step I've been stressed about the most, which is how do we heat this whole mixture once we mix it all and grind it all together? How do we heat it to 1400 degrees? Let's go get a furnace. Okay, finally, we're on to heating. So I've got this cool box here. This is, I'm going to call it my old furnace. I got this somewhat recently and have used it once or twice. Worked well for that video. Just won't get hot enough for what we need. Let's get this bad boy out. I've sort of just opened the box and that's all I've done. So what's in here? What did I buy? You know, that's one of life's greatest joys, is buying shit for yourself and then forgetting about it and then being like, wow, I know myself so well. Let's go. What do we got? Stuff and other things. I gotta get this out of the box. I can't talk while unpacking things. So let's get it out of the box. Here he is. Here's this bad boy. Look at him. He is an induction furnace. So this standard type of metal melting furnace over there will use resistive wires. So you've got this wire that you put current through and the wire gets hot and that makes the crucible hot. But if you want to go to high temperatures, you're above the melting point of the resistive wire a lot of the time. So instead, you've got to use magnets and induction. So this is what this one is, and this is why it has the higher temperature, higher maximum temperature, and why it looks a little bit more technical. Shout out to this one Nile Red short where I saw him melting steel that used this furnace. So yeah, thanks for that. Attention, do not left the heated liquid metal cooling in the graphite crucible. That seems important, but I'm not quite gathering what it means. Okay, maybe I do have to read the manual. We've got a big caution page.
Never leave hot graphite crucible with metal liquid cooling in the machine naturally.
Okay, alright, so that's what it means. So I can't just heat the metal and then leave the hot crucible in there while it's switched off. I think that's what it means, right? Grab the crucible out immediately when the melting is finished. I wonder if there's any warnings about operating this for several hours at a time. There is a water cooling line, so obviously you don't want the whole machine getting so hot that all the circuits melt, so there's this water cooling line. Okay, yeah, so this is a chiller unit, so we'll keep the water at a nice constant temperature. Oh, and this is what I've got, I guess. You've just got 2 buckets of water and it pumps cold to hot, and then your bucket will eventually run out. So you need to keep refilling the bucket. Okay, this is good. I'm learning things that will prevent my house from burning down. This is good. Speaking of my house burning down, I was going to turn this on right now, but this is a 16 amp plug. That's a lot of amps. I don't think I can plug that into the shed area without immediately blowing the circuits. So that's another consideration, I guess. All right. We've made great progress. I need to get several things before I can turn this on. All right, let's get somewhat more organized. I forgot. This higher amp circuit has a slightly different plug than your normal extension cord, so you can't actually plug them into each other. Yeah, see, it's the same shape, but the actual earth pin is bigger. So you actually need a different outlet. 15 amp or a bigger outlet. There's 16 amp, 250 volt. That's a bit weird. Let's go get a 15 amp fucking circuit. All right, just go buy more things for this. Why not? I have bought this thing, which is an adapter. Well, I don't really get the point of this. It's just making a 15 amp socket, which, like, I get, but you can still only draw 10 amps from it. Like, this was 70 bucks, and you're telling me that all it's doing is changing the plug shape, really? Isn't it just immediately going to trip as soon as it tries to draw more power? Why would this be a product that exists, and why did I buy it? Let's just see if it immediately trips the power or like the cables catch on fire or something. At least if it starts running, it might start pumping the water around, and that is at least a start. I don't think it's going to do any heating without like tripping the circuit. But then how do I power it? Anyway, let's see if this thing turns on. This plug doesn't even fit in the fucking... Alright, that's as far in as I can get the plug. Let's turn the power on. It turns on. That's a good start. Oh, I should put some water in the bucket. Alright, I'll be back. Ooh. Yeah. That didn't go well. God. Oh my God. Oh my Jesus. Lord above. But the power socket's right there. Does this tube just fit in the... Oh my God. Oh my God, that's the worst fitting imaginable. What? They've just put that in. What? Of course it's going to shoot out with the pressure. What? That's where all the power supply is. Oh my fuck. I don't know if I'm going to survive this one, if I'm going to be honest. Okay, I've fixed up the water. But I have to know, does it heat? Does it heat? 200 degrees. I don't know. This whole thing's making me very nervous. Is this watts? I thought it'd be temperature. But it's just watts. 5 kilowatts? Christ, that's a lot of power. That's too much power. That is twice what this thing is rated for. Why did I buy this? I can't run this. Alright, I've spent far too long thinking about plugs, but here we are. I have something that hopefully works now. I even posted this to Patreon and had some suggestions about this plug. Some people said it might have been Australian 20 amp plug, which I didn't even know there was a standard for. I've never seen a 20 amp plug. You know, we've got the 10 amp and then the 15 amp and then all the 3-phase, you know, circular pin ones. Familiar with that, but there's also a 20 amp one, which we thought this one might have been, but it's not even that. It is a Chinese standard. Now, you might say, well, that's obvious now in hindsight, but are 10 amp, as in Australia and China have the same 10 amp plug, but this is a Chinese 16 amp plug, which is not compatible with the Australian 15 amp system. Thank you to the online museum of plugs and sockets for this diagram that shows it's just slightly too big, which explains why I could really, if I tried, I could force it in. I changed the plug. Well, my dad changed the plug because I don't trust myself to do that much electrical work. Now this will plug into the wall, and I found it's either 10 or 16 on the circuit breaker. If it's 10 amps, trip the circuit. Tripping the circuit is bad for this because if we crank the heat, it gets hot and then the circuit breaker trips. This powers its own cooling water, so the cooling water will also stop flowing. It's not going to be able to cool itself properly, and all the water that's trapped in there will probably boil, which is an insane way of doing this, by the way. Look at this terrible, I put this tape here, but this thing doesn't sit in here, and you're kind of like, oh, it's fine, it's 12 volts, but it's not. It's a 240 volt output, which is insane because they're just putting it through a transformer to 12 volt anyway. You could make this output 12 volt, and then you wouldn't have these two 24 volt pins sitting here next to this cooling water flowing through here. Like, that's an insane design. Anyway, let's fire this bad boy up, I guess. This shocks me even once. I'm throwing it in the bin and ending the video, by the way. This shocks me even once. I'll probably die, actually, but I'm gonna have a 0 shock tolerance here. My God. What's going on? Alright. Good start. I'm also interested in how hot this cooling water gets, because if this cooling water gets very, very hot very quickly, we won't be able to run it from a bucket like this. We'll either need a much bigger reservoir or have to run it from something like a hose or something. I have a feeling it's going to get very hot very quickly, so, but just how hot? Is it a manageable hot, or is it going to be like insane? That I don't know. Alright, cooling water temperature over there, 2000 watts. Let's do it. Is it heating? Thermal camera. Yeah, alright, it's getting hotter. This lid doesn't quite fit because I'm using a slightly different crucible. I've only got one that perfectly fits, which is the one that came with it. I'm going to put proper gloves on. Let's go put gloves on. Alright. Oh, crucible is glowing hot. Glowing hot already. It's at only at 2 kilowatts. It's been about 10 minutes. Oh, these aren't the right tongs for it, but oh man. Yeah, that's getting hot. The cooling water's doing good too. It's only at 26. It's getting hotter. Alright, cooling water's getting to 31. So I think it's alright, but we do need a larger volume of water, and we'll have to change over the water a bit, especially for 6 hours. I still don't think this will run for 6 hours, but mostly I'm curious about fucking ramping this up all the way to 5, right? Let's see if we can melt some steel. How hot is this getting? This is sick. Whoa. We have a chunk of steel here. We have a melting point of about 1,500 degrees. Let's see if we can get it to melt in this crucible here. Let's try it out. Got a new bigger bucket of cooling water. Got to keep that temperature in mind. Good luck, everyone. Glowing red already. Less than 2 minutes. Oh, man. Whoops, something's on fire in there. Oh man. Lord, oh Lord. Oh, crikey. That is hot. Alright, that is setting the iron on fire. Alright. Oh. Let's turn this bad boy on. Huh. Yep. Burning the iron. Oh Lord. Yep, that's molten iron on fire. Alright. Flag down in there. Whoa. Oh yeah, that is molten iron. Well, was molten iron. Guess it kind of kills this one crucible, but I have spare, and it felt safer than pouring this out here when I was unprepared. I gotta say, I did doubt it. I was expecting it to maybe slump it eventually, but within 5 minutes to melt it like that, pretty good, pretty good. Alright, it's a beautiful day to make some yellow, and we have everything we need. We have our yttrium carbonate, we have our strangely coloured molybdenum trioxide, and our off-coloured tantalum pentoxide, and we need to mix this up, grind it up, and start heating. Here's this paper here. They first do a preheat of up to 600 degrees, which is maintained for 1 hour, and then they heat it up to the 1400 degrees for 6 hours. There's also a lot of ramping time, you know, it's 8 degrees per minute up to 600 degrees, and then 10 degrees per minute from 1600 to 1400, which is, you know, a lot of extra time. So this is a full business day worth of heating. We're not going to be able to heat it to 1400 degrees for 6 hours, but we can do the preheating in this furnace, which, you know, will take some of the work away from that other furnace, and will let us do this preheating step, which I'm going to do twice because we have this extra kind of chemical step we need to do while it's heating, which is this decomposition of the yttrium carbonate to yttrium oxide. So I'm going to heat it at 600 degrees for say half an hour or an hour or so, take it out, re-grind it, because we've got to do this solid state reaction. So making sure everything's nice and well mixed is important, and then we'll put it back in, heat it back up to 600 degrees, and then go from 600 to 1400 and keep it there for, let's try and do a whole hour of 1400 degrees. But that's red hot, you know, we're not going to be able to monitor the temperature because it's way above any device I have for monitoring temperature. My thermal camera can measure up to about 550 degrees, and even those IR monitor things don't work above 600 degrees. So 1400 degrees, way too hot. So we're just going to heat it till it's glowing and on the maximum wattage, and then keep it there, and then cool it down. Hopefully we see some yellow. As I mentioned earlier, we're going to make 2 batches, one undoped, so no tantalum, and then one with the 20% tantalum. Of course, if we read the paper, they say
It's clear from the absorption spectra of the samples that the absorption edge of the pigment dramatically shifts to longer wavelengths with increasing doping of tantalum.
so you have your undoped, and then as you're increasing the tantalum, you move this absorption edge so you're absorbing more blue light, which will make it more yellow. However, when we look at the photos, I know I've already touched on this before, but really, maybe the photos lie and the data's all right, but this is the 20% doped one, and this is the undoped one. And you might say there's a little bit of difference, or maybe it's hard with the printing, but this sample here is also an undoped one, and you can see it's the same pile of powder. So there's more difference between the same pile of powder photographed 2 different times than there is between the 20% doped and the undoped one. It's the same sample, right? We'll find this out ourselves. Who knows if this is even going to go yellow? We've got a white powder, a weirdly green powder, and a sort of a grey green powder. Is it going to make something nice, bright and yellow? Who knows? Who knows? But let's get this heat cranking. Let's get this bloody cooking. See if we can cook up some yellow. Okay, the stuff's blended into a paste. The starting materials weren't that wet. They weren't completely dry, but maybe the acidic oxide reacted with the carbonate already. Whatever. We're just going to keep going. I mean, it's going to go to high temperatures. It's just hard to mix when it's pasty, but this ain't stopping us. Do you like my yellow pigment? Are you impressed by it? Had 10 minutes at 600 degrees. Ooh. Oh yeah, there's some yellow already. Doped one out, get this undoped one back in after grinding. I've set it to 800 degrees now, just a bit hotter. We'll let it cook at this temperature for a little bit. This is the doped one, looking pretty similar so far. Alright, the undoped one's been at 800 degrees for the last hour or so. Let's get him out and let's get him up to 1400 now. Get this doped one heating in the meantime. Let's go really heat this. Oh, it's getting really yellow. I don't know if it's just glowing, but it seems really yellow in there. Alright, I've preheated this one just a little already. Not that hot, just a little. Start the heating. Just keep an eye on the temperature of the water bath. Can't let that get too high, as we know, but we'll step this through. We'll go to 2000, 2600, and then we'll go to the full 5000 soon. It's still only 2600, but could be hot enough already. It looks hot. It's hot. Oh, that's bright. Oh, this has probably fucked my thermal camera, but nearly fucked my eyes. That's hot. That is hot. Smoking a lot though, so I'll just leave it like this. Oh, it's only on half power. That is hot. My goodness. All right, we're 10 minutes in, and that water as it's coming in, or the return water, is steaming a little. Don't know if you can see that, but whoa, ow, that's hot. It's hot, the return water. All right, we're gonna have to modulate the heating a little. Let's even turn it off for a moment. All right, the cooling water outlet is only slightly warm now. It's been off for about 5 minutes. So let's get it cranking again. Maybe a little higher. 4000. Let's just give this a shot. What's it look like, by the way? Yeah, everything's kind of on fire, but let's go. Heating button. Ooh, what's that noise? Ooh. Oh, I can't look at that. I can't look at it. Oh, I need sunglasses. I'm seeing spots, man. That's psycho. All right, I'm gonna swap over the materials. I've got the undoped one fresh out of the other furnace. This graphite crucible was a lot easier to pick up than this other one. This other one doesn't have the groove in it. fucking sucks to pick up. It's cooled down a little bit in here. The water's not too hot. Might heat it again a bit later. Give it another burst of heat, but getting this other one cooking. Can't tell the colour yet, still just glowing red in there. Anyway, we'll get this guy in. Oh, it doesn't quite fit. Oh no. Alright, best of luck to this guy. The cooling water is steaming again. Oh, that's... Yeah. Alright. We'll give it a moment. We'll give it a moment. Alright, it's still heating everything, but this is our undoped one. It's just cooled down enough to see the colour. Oh no. Oh no. Hold on, let me turn the flashlight on. All this work, and we fucking burnt this to shit. What the fuck? It was looking kind of yellow. It was looking really yellow. Did we get it too hot? What's happened? Oh, we've absolutely cooked this. Oh no. Oh no. Let's save the other one. Oh no. That's my whole batch. Oh no. Oh, quick. Oh god. We've got to stop this. Oh, I hope I didn't cook this one too. In all my thinking, I didn't think I'd get it too hot. That was not something I thought would happen. Oh no, I barely heated this one and it started to go black too. Oh, it was pretty yellow before I put it in the insane furnace. Oh no. Oh no. Oh no, alright. I got time for another batch, one more batch. Let's ditch this black stuff. I'll make an undoped batch. Let's just not get it so hot. We can't get it so hot. Oh man. Here's our second batch of undoped. We are taking it all the way up to 1,000. It's already had half an hour at 700 degrees, and then I've took it out and reground it. And so we're gonna see, hopefully it's stable up to 1,000 degrees here in this furnace, and then we can go over to the other furnace if we wanna see if we can get it even more yellow. But let's see how yellow it gets after heating to 1,000, because we don't wanna overdo it like we did the last batch. Okay, this undoped one has been at 1,000 degrees for a little bit now. Let's grab them out. Ooh. And I can't tell the colour because it's just all red hot, but it's basically on fire. Okay. Yeah, cool. Alright. Is it on fire? Interesting. Alright, well, I'm just gonna let that go. And then I'm gonna get this the doped one heating, and once that stops being red hot, we can actually try and see the colour on it. It's looking good. It doesn't look too black, but pretty hard to tell when it's just glowing bright orange like that. Get it away. Oh yeah, see, look at that. That's a fantastic yellow. Well, I mean, it's not quite as vibrant as the paper is, but once again, we've only taken it up to 1,000 degrees, so I do want to take it up higher. My theory is why it went black was not because it was too hot, but because of the graphite. The graphite at 1,500 degrees is extremely reactive and very reducing, so I think it's pulling the oxygen out of the structure, out of the oxides, and reducing it back to the metal. Well, like molybdenum, it's just that powerful reducing agent at that temperature. So I really want to move to a different crucible. I don't really have a nice crucible like this, and I'm not sure if I use a different crucible, will it work in the induction furnace? Does it have to be conductive for it to work? Let's give it a shot. Let's try and do this in a way where we can heat this powder up to the 1500 degrees or 1400 degrees or so, just in this thing. But we don't want it to shatter, so we're gonna have to take it a little easier. But that's what we're doing. It's obviously getting nighttime, but also have a doped sample cooking. I just had enough yttrium to do a half batch of some tantalum doped one. So let's get this, it's still very hot, but let's get this yellow powder, our 1000 degrees powder, into here, and then let's see if we can heat this, you know, with the powder in it, up to the higher temperature that we need. Well, that's what I think we need. I don't know. Maybe this is as good as it gets, but I'm getting greedy here. Everything is horribly out of focus, but that's how I'm feeling right now anyway, so it feels appropriate. It's not working. Even when this stuff gets red hot, the heat transfer is so bad that this doesn't even get to 400 degrees. I really need it in there. I need it in the base there where it's really hot, but how can I do that? Can't put it in steel because the steel will melt, glass will melt, quartz will get fucked up, I think, especially this rapid heating and cooling. I'm going to put this ceramic plug down at the bottom of this. It's all I can think to do. Hopefully it stops a lot of the material touching the carbon and we can still heat it to a high temperature. That's all I can think to do, really. Alright, looking good. Turning heat back on now. Turn the heat off, give it a bit of time. I've been pulsing it on and off at the full wattage. You can't see shit on the camera. Oh man, there's so much infrared radiation coming off that this camera sensor is overwhelmed. But I think everything is absolutely cooked except for the little bit that's on the ceramic tile in there. There's a little pile of powder that hasn't touched the graphite, but has been getting really hot, obviously, down in there. So, yeah, sorry about all this noise. I can't turn it off because if I turn it off, the water cooling stops, and then it'll die. Anyway, let's let this cool down so we can actually start to see what's in there. Oh man. Oh man. Yeah, sorta. Yeah. Dunno. And in the daylight here, we can assess the damage. Look how black this sample is. We really burnt it. But if we kept it at 1000 degrees, the samples didn't stay yellow. Even though they looked yellow when they were red hot, and I think they might have actually been yellow. On cooling, they went back to white, didn't retain their yellow color. But we did manage one sample. Look at this. This was a sample that was balanced on a little bit of this crucible. It didn't touch the graphite. Maybe it's not as simple as that. Maybe it just didn't get too hot. So maybe these samples got to 1500 degrees and that was just too hot and causes decomposition. Whereas 1400 degrees is hot enough to cause it to go yellow, but not enough to make it go black. Or it proves a point that even if you think the science is a little bit stupid, doesn't make it easy. Science is still difficult. It's going to be yellow for all eternity. It's been yellow for the last 2 weeks, so it's going to be yellow for all time. There's enough here to do my true purpose for this video. Painting a picture of my cat. Alright everyone, I hope you enjoyed this video as much as I did. Well, I'll see you next time. Oh, I forgot I can't paint.